Hi everyone, it's a pleasure having you here. I'm Manuel, and for the next 10 minutes, more or less, I will be talking about the formation of intermediate mass black hole and stellar black hole mergers in dense star clusters. The results I'm going to describe are discussed in these two papers, and these have been done in collaboration with the people listed here. In this brief talk, I'd like to make three main points. One is about IMBH formation. The next is about the development of IMBH black hole mergers in dense clusters. And the last one is about the perspectives for current and future gravitational wave detectors. In the first part of the talk, I will focus on a series of direct n-body simulations of young massive clusters that included GR effects to model the evolution of binary compact objects. These simulations are discussed in Rizzuto et al. 2021, so please have a look at the paper. And unfortunately, these simulations included all the relevant physics, but a treatment for gravitational wave recoil and spins. Yet, in 17 cases out of 80, we found the formation of an IMBH, corresponding to a formation probability of around 20%. In a bunch of cases, the IMBH was either the result of a series of mergers among stellar black holes, or was forming somehow and later was capturing a stellar black hole and merging with it within ample time. So given the absence of recoils and spin, we decided to extract these potentially interesting candidates and to study the impact of such quantities on the long-term evolution of IMBHs. And now the type of interactions we selected are listed here. So as I said, an IMBH in these simulations form mainly through two main channels. One is actually very rare and is shown in the left side of the two panels. We have a merger where the primary is the result of a series of merger among black holes, while the companion is the result of accretion of a red giant star onto a stellar black hole. The final merger leaves behind an IMBH with a mass of 140 solar masses. And if you look at the masses involved, you will immediately see a nice compatibility with the masses inferred for GW19521, which is basically the first IMBH detected through gravitational waves so far, thanks to the LIGO-Virgo collaboration. Now, today I don't have any time to discuss in detail this channel, so if you are interested, please have a look at the paper or reach me out with any questions you have in mind. In fact, today we are going to focus on the other channel, which is way the more common in these simulations. And basically is schematized here. You have a sequence of stellar collisions among massive stars. The final massive star ultimately is accreted onto a stellar mass black hole, and this leaves behind an IMBH seed. In a few cases, this IMBH seed captures one black hole and merges with it in a few hundred mega years, and in one specific case, this happens twice, and this is the one shown here in this panel. For the sake of clarity, I will identify different generation mergers with numbers 1, 2, 3, and the primary with letter A, 1A, 2A, 3A. And in the next slide, we will focus about one single aspect of this merger tree, that is the evolution of the IMBH spin. In fact, we don't know almost anything about IMBH spins from the perspective of IMBH formation, because this is something obscure yet in black hole physics, how IMBHs do form and where and when and why. So we decided to make an agnostic study where our IMBH seed formed out of accretion of a stellar component onto a stellar mass black hole is either non-spinning or nearly extremal. The non-spinning case is marked with color blue, and the orange marks the nearly extremal case. And what you see in this panel is the remnant spin of the first generation merger. So what is left behind? This is the spin distribution. If you have a non-rotating black hole, you see that the final spin is narrowly peaked around 0.2, whereas for a nearly extremal black hole, the spin distributes widely between 0.6 and 1. One thing that is sure here is that you can clearly distinguish the two extreme cases of a non-rotating or nearly maximal IMBH. And this means if your IMBH is ejected away from the cluster after a merging event, its spin will be frozen in time, and measuring it will give us crucial insights on the history of that IMBH, whether it was for instance, a slowly spinning or a nearly extremal one, and this can help in disentangling different formation scenarios and placing constraints on them. Now the question is whether this peculiarity preserves upon multiple merger. So first we took the one case in our simulations where the remnant of such merger undergoes a further merging event, and this is what we get. In the right side of the panel, you see again what happens for an initially non-rotating black hole or for a nearly extremal. You see yet that basically all non-rotating IMBHs end up with a spin below 0.4, and almost all the initially extremal IMBHs will have a spin above 0.4. So still you can clearly distinguish the two extreme cases. And this is really a powerful possibility to disentangle different formation channel and scenarios about IMBHs. Unfortunately, we have just a handful cases out of 80 models, and this gives you immediately an idea of how many models we would need to get a statistically significant sample of them. Unfortunately, the number is limited by the cost of direct embodied models that enables you to have a few models per month if you are very lucky. And so usually these models are combined with other techniques that helps you pinning down the region of the phase space where you really need the high accuracy of embodied models. So in the last part of the talk, I want to focus on a combination of two techniques, semi-analytic and few body, that can be readily connected and compared with the direct embodied that we just saw here. For me, few body means three in this case. We have one IMBH orbited by two stellar mass black holes, and this triple initially is built with no hierarchy at all, and is embedded into the potential well of a star cluster. We model this triple in the cluster potential, including PN effects, and we study whether and when a merger can occur and how. And given the low cost of these simulations, we've been able to run thousands of them at varying different parameters like the IMBH mass or the black hole mass spectrum. And what we get is that basically the three-body phase ends up most of the time with the ejection of one of the stellar black hole, and the last phase is basically an IMRI phase where the IMBH and the black hole ultimately merge. Interestingly, on average, these mergers that we find in our simulation are low eccentricity mergers, even when they sweep through the Lisa band. And the probability for this merger to occur ranges between 5 and 50%, depending on the assumptions made. Then we took these results and we put it in a semi-analytic machinery to calculate the probability that this three-body IMRI phase occurs more and more during the lifetime of a cluster. We included kicks to calculate whether or not the remnant can be retained, and we set a limit on the maximum number of black holes that can participate in this process. And then we made some assumption on the cosmology of star clusters. We assume that they can form within redshift 2 and 6, and we assume that IMBH seed masses range between 100 and 500 solar masses, which basically bracket the range of values we found with Ritsuto et al. Simulations. And we assume that star cluster mass distributes according to a power law as suggested by observations. So with the semi-analytic machinery and these assumptions, we've been able to calculate the evolution in time of IMBH mass and spins that is shown here at varying the redshift, and particularly at redshift below 1, which are the yellow steps, we see that the IMBH masses peaks around 750 and the spin peaks around 0.3. This on a side means that actually the growth of IMBH's true repeated black hole mergers is limited from the cluster mass spectrum and from the efficiency of merger, and that the spin is relatively small. So in the future, having observations of such system can be really helpful to disentangle whether this channel can dominate or not IMBH growth. And whether you can observe them depends on the gravitational wave detector. So we calculated the signal to noise ratio for LISA, first of all, close to us, within 8 kiloparsec, because within this radius we actually have a bunch of candidates, the globular clusters candidates that might host an IMBH, plus the galactic center that might contain a couple, if not more, IMBH candidates. And we measured a signal to noise ratio over a 4-year observation time between 6 and 100. So it's really promising for us to having LISA probing IMBHs in the Milky Way. And in a more general perspective, we also calculated the merger rate for different detectors across different redshifts. And what you see in the panel here is the cumulative merger rate at different redshifts for different detectors. And here, the most important unknown that need to be modeled is the number of IMRIs per unit IMBH mass, which depends on many unknown. So we used the 3 different approaches to calculate it. And in the end, we got actually pretty consistent results. So it seems that the result is almost model independent. And if you transform the results into numbers, you get this table here that shows you that LIGO and Virgo should be able to deliver 1-2 IMRIs with a mass below 200 solar masses in 1 year of observation. So we really look forward to 2 or 3. LISA can deliver up to 60 events per year. And the Einstein telescope and DECIGO should reach 1,000 of detection per year when they will be operative. So it seems that the next 2 decades are going to be extremely exciting for people working in the field of IMBH, and we really look forward to it. And with this last thing, I'd like to leave you with my take-home messages, and I really look forward to meet you all in person and to get soon your questions. I'll be happy to answer any of them. Thank you so much for your attention, and see you. Bye.